our question for here. What can we do if we're unable to diagonalize a square matrix? Our focus will be when our eigenvalues are not in our base field. So if I have real vector spaces, what happens when we have complex eigenvalues? Now, our setup, I'll have a linear transformation T from Rn to Rn. Can represent T by a square matrix A. If I want to diagonalize A, our first step is to look for eigenvalues and eigenvectors. So we're trying to solve the characteristic equation. To do that, we first find the eigenvalues. So we would set up the characteristic polynomial. Then we would find its zeros, and those are the eigenvalues. Once we have those, we can find our eigenspaces by computing each null space A minus lambda I, where lambda is an eigenvalue. Now, what can go wrong? First, it might turn out that our eigenvalues are not in our base field. So that's what we want to address here. Even if all of our eigenvalues land in our base field, we still have to worry about finding a basis of eigenvectors. Okay, and that's a question for a second linear algebra class. Now, the answer to both of these is going to hinge on invariant subspaces. So, definition, suppose I have a subspace W in Rn. I'll call it invariant under A. If, whenever I have a vector W in our subspace, A on W is going to go back into our subspace. So the idea here is W is going to be a subspace. If we hit it with A, it just maps back into itself. Now, the example you should put with this, okay, just think of what happens with eigenvectors. So if I take V, a non-zero eigenvector for A, okay, I'll take its span. So that's going to be a line through the origin in Rn. If I apply A to any vector in here, so they're just going to be the multiples of V, well, V is an eigenvector, so we're just going to take our V and multiply by a scalar. So this is going to land on that line again, and so we have an invariant subspace here. So we're just trying to generalize the idea of an eigenspace. Let's state our main result. So let A be an n by n matrix with real entries. In Rn, there exists at least one of the following: a non-zero eigenvector for A, or a two-dimensional subspace invariant under A. So that'll be an invariant plane. Now, how does this result help us? For real matrices, it's often convenient to prove results by going to complex vector spaces. If I'm working in the context of real vector spaces, those proofs would be off limits. So we would need a workaround for what to do when complex numbers show up. So our result is going to be a workaround for when we have to deal with complex eigenvalues. Now, let's take a look at the characteristic polynomial. So, if A is a matrix with real entries, then this is going to be degree n with real coefficients. If we factor over the complex numbers, then all of our factors are going to be of the form lambda minus c, where c is a complex number, raised to some exponent. If we insist on factoring over the real numbers, then we get two types of terms. We'll still have terms of the form lambda minus a real number raised to some power, but we'll also have terms that are irreducible quadratics. So they will be of the form lambda squared plus a lambda plus b, where a and b are real, we raise to some power. For our irreducible quadratics, the roots are going to occur in conjugate pairs. So you can see that using the quadratic equation. So what's happening is, when we go from the complex factorization to the real factorization, these conjugate pairs have to come together so that we get only real coefficients. Now, the reason we bring this up, okay, you want to pay attention to how these factors show up in our proofs. So the idea is, if our irreducible factor has an exponent of 1, then I get an eigenvector, one-dimensional invariant subspace. If I have an exponent of 2, then we're going to wind up getting a two-dimensional subspace. That's invariant. Let's note some facts about the invariant subspace V. First, invariance is the correct condition for restriction. So, if I restrict a linear transformation to a subspace, if I want to study this, I would want that our subspace is carried back to itself, and that's what we get from invariance. So invariance is going to let us go from the big picture to these smaller pictures. Then, if we choose a basis V1 through Vk for our invariant subspace, we can complete that to a basis for Rn, and then we can consider what our matrix A looks like when we change basis. Now, the recipe for the new matrix: for each basis vector, we're going to assign a column. The numbers in that column are going to tell us how to set the linear combination for the image of our basis vector under A. So, if I take one from our invariant subspace, say V1, V1 will be sent to a linear combination of V1 through Vk. All the coefficients for Vk plus 1 through Vn are going to be 0. That means in this block here, we'll have whatever comes out from the linear combinations, but we're guaranteed to have a block of zeros directly below. For Vk plus 1 through Vn, we don't have any information, so all we can say is block and block. Now, that means if we have an invariant subspace, we could choose our basis so that the matrix for A with respect to our new basis is block upper triangular. Once we have that, we'll have the following result, which states, okay, the characteristic polynomial for the restriction will divide the characteristic polynomial for A. Now, that'll follow because we have these blocks here. So, the characteristic polynomial for A is independent of change of basis, so I can compute it using our matrix here, and then we would have the characteristic polynomial of this matrix is just the characteristic polynomial of this block times the characteristic polynomial for this block. Let's see why our result is true. We know how to find eigenspaces, so let's assume there are none. Then there are no linear factors in the characteristic polynomial, so we'll only find powers of irreducible quadratics. Choose a non-zero V in Rn. We'll form the invariant subspace, capital V equal to span of V, A squared V, A to the k minus 1V, where I choose k such that our set is linearly independent, but if we add A to the kV, we get a linearly dependent set. Now, because we're working Rn, that means k is less than or equal to n. By the linear dependence, we'll have that if we add A to the kv to this set, some linear combination is going to be equal to 0. Okay, we can arrange the coefficient of A to the kv to be equal to 1. That means there's some polynomial of degree k in our matrix A, such that if we apply to V, we get 0. And by linear independence, we can't have that happen for any lower degree polynomial, except for 0. Now, how do I get invariance? Well, note, if I apply A to any of these basis vectors, we'll have, okay, V going to AV goes to A squared V, no problem until I get to A to the k minus 1V, which goes to A to the kV. But by this linear combination here, I could push all these terms to the other side, so A to the kV is just going to be a linear combination of all the previous vectors. So that shows that V is invariant. Taking a closer look at our polynomial, we've seen that the degree is less than or equal to n, but we also have that it's greater than or equal to 2. To see that, chosen V to be non-zero. If V and AV are linearly dependent, then AV is some multiple of V, so V is an eigenvector for A. We're assuming that can't happen, so that means our degree is greater than or equal to 2. Now, let's write our polynomial p in the variable lambda. We're going to factor completely over the reals. So the q's are going to be irreducible factors with some exponents. Our irreducible factors are either linear factors or irreducible quadratics. Now, if we try to bring the exponents down, I take that polynomial, we apply it to a, then apply that to v. By linear independence, we'll get something that's non-zero. So, if we have a linear factor, say lambda minus c, okay, we'll bring it down by 1. I'll define w to be equal to that polynomial, applied to a, applied to v. By our recipe here, this is non-zero. If we apply qi applied to a to w, okay, that's just a minus ci, we'll get 0 because we're just looking at p applied to a, applied to v. So I'll have an eigenvector that's non-zero for eigenvalue c. We're assuming that can't happen, so that means we're going to have no linear factors in our factorization. So they're all irreducible quadratics. Since the degree is greater than or equal to 2, we have at least 1. So I'll call that Q1. Now, I'll use the same trick. We're going to take W equal to P divided by Q1, applied to A, applied to our V. So our recipe says this is a non-zero vector. And we also have that's in the null space of Q1 applied to A. So if I multiply by Q1 applied to A, we're just looking at P of A applied to V, which is 0. Also, if I take the span of W and AW, we're going to have an invariant subspace by the same reasoning we used here. Now that we have our result, let's show that Q1 divides the characteristic polynomial of A. So, our Q1 is an irreducible quadratic. We found a non-zero W in the null space of Q1 applied to A. And with that, we found our invariant plane by just taking the span of W and AW. Now, because W is in this null space, I get this equation here. So we'll have that A squared W is a linear combination of AW and W. If we choose a basis for Rn that starts with W and AW, we can represent A as a block upper triangular matrix. And note, okay, W is going to be sent to AW, so the first column is 0, 1, and all zeros. AW is sent to A squared W, so we'll have, okay, minus B, minus A, and then all zeros. And then for the rest, we would need more information. So if we take the characteristic polynomial of A, we're going to have characteristic polynomial of this block times characteristic polynomial of this block. The characteristic polynomial of this block, when we work it out, is just going to be Q1 of lambda. So that means Q1 divides the characteristic polynomial of A. Now, that's just a method for finding invariant planes associated to irreducible quadratics in the characteristic polynomial. These will just be the invariant planes that contain no eigenvectors. So, take the characteristic polynomial of A, factor it completely into irreducibles. We would choose an irreducible quadratic, say Q. Then we look for a non-zero W in the null space of QA. So, we haven't shown that we can always do this, but it'll always happen. So that's a question for linear algebra 2. Then I could form an invariant plane by taking the span of W and AW. For a concrete example, let's consider the following A. So note, you can get 2 invariant planes just by observation, but we want to push this through the machinery. So we find the characteristic polynomial of our A. That'll factor into lambda squared plus 1 times lambda squared minus 2 lambda plus 2. Here, our eigenvalues are going to be plus or minus I, 1 plus or minus I. So we have no real eigenvalues. if we let q be equal to our second factor, then we're going to look for a non-zero w in the null space, a squared minus 2a plus 2i. So that works out to this matrix here. And for a non-zero w, I'm just going to choose the second standard basis vector, 0, 1, 0, 0. If we apply a to that vector, we're just picking off the second column. So I'll have 0, 4, minus 5, 0. This set is linearly independent. Now, if I apply a to aw, I get a squared w, which is equal to 0, 6, minus 10, 0. We verified that's equal to 2aw minus 2w. So if I push these terms over to the left side, we note our irreducible quadratic reappears, as expected.